Swayam Prabha. Digital India. Educated India.
So in this lecture, we are going to look at a very important reaction known as the electrophilic aromatic substitution. We already have a good idea about the way aromatic systems are going to react, and so we'll now look at some of these reactions in detail. So in the past couple of introductory lectures, we have seen the value of NMR, both proton NMR as well as carbon NMR, and how it is very useful for us to understand structure of molecules and what is the local environment, etc. So now what I'm going to do in the next minute or so, couple of minutes or so, is to describe an NMR experiment that we do. Okay. So what we do is we take basically phenol, whose structure is shown here. It's benzene with an hydroxyl group, and we dissolve it in D2O. Okay, D2O is basically deuterated water, and deuterated water, and the concept that we need to understand, which I will now discuss, is that deuterium is NMR silent. Okay, which means that under the conditions under which you do proton NMR recording of proton NMR spectrum, deuterium is silent. So once you replace hydrogen with deuterium, that peak will disappear. Okay. So when you add phenol into D2O, the pK of phenol is a little bit above, around maybe 9, 10 or so. And so in D2O, what happens is that there's an equilibrium that's set up between this phenol and phenoxide. And right, O minus, and once this equilibrium is set up, when it picks up the deuterium, it goes to OD rather than OH. Okay, so of course this is also going to be an equilibrium in this reaction. So gradually phenol gets completely converted to deuterated phenol. So in the NMR spectrum, the peak that you would expect for OH doesn't show up, and so you see only the remainder of the peaks. Now coming to the remainder of the molecule, let's look at this one by one. Okay, so when you look at phenol, this position, let me just number the carbon so that it's easy for us to follow it. So this is 1, 2, 3, 4, 5 and 6. Okay, so in carbon number 1, where the hydroxyl group is there is no hydrogen, so there is nothing to worry about here. When we look at carbon 2, there is a hydrogen attached to it, which I've shown in red. Okay, and you will see that there is a plane of symmetry in this molecule, and this plane of symmetry which I'm going to just draw like this, sort of cuts the molecule into two. Okay, and therefore this part of the molecule, the left hand side of the molecule, is identical to the right hand side of the molecule. Okay, so the one that I have circled now, these two hydrogens are the same. So the chemical environment is the same, and therefore they also show up in the NMR as a single peak. The magnetic environment is also the same. Now the next set of hydrogens, which are in green, are also the same. Okay, and lastly there is one hydrogen here that I'm showing in the form of a square, that is a single hydrogen anyway, and it's distinct from the other hydrogens. The other way to think about it is that if I assume that from benzene I am making phenol in my mind, the hydrogen here is close to the phenol, and therefore the environment that it's going to experience is going to be different. from this hydrogen here, which is a little bit far away from the phenol. And lastly, this hydrogen is in the 4 position, and therefore it must be experiencing a very different environment. And among these 3 hydrogens, not just the phenol, but this hydrogen is next to the pink hydrogen here, and this hydrogen here, the hydrogen is also next to this hydrogen here. Whereas this red hydrogen is only next to the phenol and the other hydrogen. So there are many differences that you can sort of systematically work out. But at the end of it, what we realize is that the phenol in D2O has 3 distinct signals that we would expect to see, which I'm going to label here as HA, HB, and HC. So just to be clear about the numbering, this is 1, 2, 3, 4, 5, and 6. So you're going to see 3 signals in the NMR spectrum. I'm not going to draw out the NMR spectrum because it's a little complicated, and we have not done coupling, for example, in NMR, so that will be reserved for an advanced course. But suffice to say that you do see 3 signals in D2O. Now the experiment that we want to do is we take phenol or deuterated phenol in D2O, and add some amount of D plus. D plus is basically the equivalent of H plus, except that it is a deuterium. Now, as we just discussed this, then you record the NMR spectrum. It's an NMR experiment, and what you expect to see is essentially the peaks that you expect to see are this OH is going to be replaced by OD, so that becomes NMR silent. Now the HA, HB, and HC are the 3 peaks that you expect to see. However, when you go and record the NMR spectrum, what ends up happening is that you don't see a peak for HA and you don't see a peak for HC, but you only see a peak for HB. Now remember that we discussed about the formation, the replacement of hydrogen by deuterium and how that's going to have an effect on the absence of a signal. So if deuterium replaces hydrogen, then it's going to become NMR silent. So one possible interpretation from this experiment is that under these conditions, this is actually forming a molecule like this. So what happens if I just draw out the original structure that we had was OD, H, H, H. So as we discussed, this is A, B, and C. So now this A is replaced by deuterium, C is replaced by deuterium, and so therefore you have only one signal in the NMR spectrum when you add D2O and D plus. So this is a very important experiment because this tells us that there is a substitution reaction that is happening. So first of all, the aromatic ring is involved, so therefore it's an aromatic reaction. The second key term is the substitution that is happening. So you have a deuterium that is replacing hydrogen, and therefore it is a substitution reaction. So as a reaction, we are going to call it as an aromatic substitution reaction. Now the mechanism of the reaction, or the way in which the reaction happens, we will understand that it's actually an electrophilic aromatic substitution. So now let's try and understand the mechanism of this reaction. So before we get into the details of the mechanism, let me introduce another reaction to you. So you all must be familiar that if we start with a cyclohexene and add bromine to it, we get this 1,2 dibromo compound, and this is a very standard reaction that we're all quite familiar with. Similarly, if you start with a peracid such as MCPBA, okay, we end up with the corresponding epoxide. Okay, so these are all fairly well established reactions of olefins. But when we do the same, expose benzene to the same reaction conditions, okay, that is bromine or MCPBA, there's absolutely no reaction. Okay, so benzene is fairly stable and it really doesn't do the kind of reactions sometimes that olefins do very easily. Okay, you also would have studied it as a very special property of aromatic compounds, which is that 4n plus 2 pi electrons, etc. Okay, so now how do we get benzene to undergo bromination? If we want to do that, then what we need to do is basically take bromine and add some Lewis acid like aluminum chloride, and this reaction goes fairly well. You get the product, which is bromobenzene. Okay, now if I look at this reaction, we can clearly say that this is an aromatic substitution reaction, as we discussed in the previous case. Okay, because the hydrogen here is being replaced by bromine. Okay, now here comes the question about the mechanism. Okay, so in order to understand the mechanism, let's first move to the reaction where we had the olefin. Okay, so you're all familiar with the bromination reaction. So you have Br, and then this you can push arrows here, and you get to the cyclic bromonium ion, which then eventually gives you the dibromo product. Okay, through the addition of Br minus. Okay, so now similarly, so this is called an electrophilic addition reaction, because if you see, the bromine has actually added on to the olefin here. So this is an electrophilic because the olefin is reacting, or the carbon based group is reacting as an electrophile. So therefore it's an electrophilic addition reaction. Okay, and it's also it's also called as bromination, epoxidation, whatever those reactions, they all come under electrophilic addition reactions. But the important point here is that there is an electrophile that is produced, which is essentially Br plus. Okay, so this is important that we understand, because the active reacting group is not bromide, but it is Br plus. Okay, now coming back to the aromatic substitution reaction that we have just encountered. So in the case where we had Br2 and AlCl3, what we can propose based on our knowledge of chemistry so far is that we can say that the Br, which has a pair of electrons, can coordinate with AlCl3. Okay, once this coordination happens, it is going to produce a complex such as this, where you have AlCl3, and you're going to have a full positive charge on Br and a negative charge on aluminum. And what can happen is that this produces a very reactive species. Okay, so this is the reactive electrophile that's going to react. Now let me move to the next slide where we can discuss this in a bit of detail. So let me just draw out the benzene ring, and here is your Br, and AlCl3. So there's a negative charge on aluminium, there's a positive charge on Br because Br is donating electrons to aluminium. Now this is set up beautifully to do the electrophilic aromatic substitution reaction. Here is where it attacks, and then this kicks out this leaving group here. Okay, so what I will do now is I'll just number these carbons so that it's easy for us to follow. This is 1, 2, 3, 4, 5, and 6. Okay, so if we just redraw the benzene ring the way it is, now what is going on here is the bond between 1 and 2 is being broken, and a new bond between 2 and Br is being formed. So let me just draw out the new bond Br, and as you can very clearly see, the byproduct is Br AlCl3, and it has a negative charge because once this lone pair goes here, there's still a negative charge that's remaining. Okay, so the bond between carbon 2 and bromine is being formed, and there's the bond between 1 and 2 that is broken, and that would result in a full positive charge on carbon 1. Okay, the remaining bonds will continue because you will get, the other double bonds are going to remain, and keep in mind that this hydrogen over here remains at the 2 position. So let me just draw this hydrogen out as well so that it's easy for us to follow it. So this is carbon 1, 2, 3, 4, and so on. So these 2 hydrogens, all the hydrogens remain intact. So far hydrogen has not been lost. Okay, so this is the step where this is called the addition of E plus, which is the electrophile. Okay, the next step, which I'm going to draw out here, the next step is the elimination reaction, which is a loss of a proton. So let's look at that step now. So I'm essentially drawing the same structure that I drew in the previous page. There's a positive charge here. Keep in mind that this is 1, 2, 3, 4, 5, and 6. And there's a double bond here, there's a double bond here, and there are resonating forms that we can look at later. But now imagine that there is either a bromide or water or something in the system that comes and attacks here and produces, reforms the double bond. Then the product that you get is this bond remains the same, this bond remains the same, Br carbon bromine bond remains the same, and there's a new bond that has been formed here, and HBr is lost. Okay, this could also be water or it could be any other nucleophile or base. Okay, so if you look at here closely, you should be very careful with this because the numbering is very important. So I'm just keeping the numbering the same just so that we understand the reaction outcome. So there's now a bond that's been formed between carbon 1 and carbon 2. That is a double bond. All right. So this is actually is an elimination reaction. Okay. So therefore, this substitution reaction is actually a combination of the substitution is equal to addition plus elimination. Okay, so that's why this reaction mechanism is quite unique. Okay, now coming to the resonance forms. So if I take a general structure such as this E and H, and I'm just going to stick to the same numbering, or I'll just change. This is 1, 2, 3, 4, 5, 6. and the positive charge is here, the double bond here, double bond here. Okay, so now you could draw a resonance form wherein I'm just going to put this positive charge outside so that it's easy for us to follow, and this becomes carbon 1. Okay, so one way to draw a resonance form is to push this electrons over here. Okay, so when you push the electrons over there, the resulting structure has exactly the same structure, except that there's a new double bond that's being formed here, and there would be a positive charge here. This double bond remains intact. Okay, so just to complete the numbering, this is 1, 2, 3, 4, 5, and 6. Okay, and lastly, if you push these electrons over here, then you have a full positive charge here, E, H, and so on. Okay, so again, if I stick to the same numbering, 1, 2, 3, 4, 5, and 6. Okay, so these are the resonance forms that could happen in the intermediate that sort of stabilizes the positive charge that is present. Okay, now let's look at a slightly different reaction, which is basically the nitration reaction. So again, this is something that we might have encountered earlier in our previous courses, but it's a very important reaction that we understand. So when we add HNO3 and H2SO4, the product that we get here is nitrobenzene. Okay, so let me just quickly write out the structure of HNO3. All right, now what happens is that this picks up a proton from likely from H2SO4, SO3H, okay, and the product that is formed is actually N double bond O, OH2 plus OH, and you can push arrows for water to leave, and the electrophile that is going to be produced is N double bond O, double bond O, H plus. Okay, so the other way to if this is going to lose a proton, then the electrophile that you're going to produce would be there's a full positive charge here, sorry about that. The electrophile that is going to be produced is NO2 plus. Okay, now this NO2 plus is the active nitrating agent, and the reaction that it can undergo, it can mediate, is the reaction with the benzene ring. So let's now draw that out. N double bond O plus, this can attack here and this moves up, and you get H, N double bond O, O minus, and this nitrogen continues to have a positive charge because it has 4 bonds and there is a full positive charge on this carbon. These 2 bonds remain the same. Okay, now as we discussed earlier, you can propose that a base of some sort, which could be HSO3 minus, for example, comes in, picks up this proton, and the final product that you're going to get is nitrobenzene. Okay, so this is a fairly straightforward reaction mechanism once we have understood the basics.